Good day, everyone. I'm Maria Victoria Migo-Sumagang, and I'm presenting a paper entitled A Superstructure Model for Integrated Deployment of Negative Emissions Technologies Under Resource Constraints. This work is authored by myself, Professor Kathleen Aviso, Dr. Frederick Tapia, and Professor Raymond, and we are from the De La Salle University, Philippines. The presentation is organized into four parts, and we will begin with a discussion on negative emission technologies. The entire world is now focused on climate change mitigation to reach the Paris Agreement targets. This graph shows the road to achieve 1.5 degrees target by the year 2100, and the pathways examined by IPCC show that we need to reach net zero carbon dioxide emissions by the mid-century in order to reach this target. Several countries have already pledged net zero emissions by 2050 at the UN Climate Change Conference in 2019. But to attain net zero emissions, some form of carbon removal is required. And we call these carbon removal technologies negative emission technologies or NETs. Let's remove carbon from the atmosphere so that the resulting atmospheric concentrations are lower before their deployment. The exact amount of negative emissions target in the next decades is highly dependent on the decarbonization of different sectors. These are examples of terrestrial or land-based nets. Nets that rely on biomass include afforestation and reforestation or AR, wetland restoration, soil carbon sequestration or SES, biochar, bioenergy with carbon capture and storage or BECCS. An example of net that uses inorganic reaction by applying crushed rocks to land is enhanced weathering or EW. And an example of net that uses engineered solutions include direct air capture or DAC. With the rising popularity of nets, the negative emission capacities, environmental impacts, and cost of nets have been assessed in various literature. For example, Smith and colleagues studied the impacts and costs of nets on a per ton carbon equivalent basis. They reported a range of values, but for this table, it's just showing the lower impact values. They studied the impacts of nets on resources such as land use, water use, energy input, nutrients, specifically nitrogen and phosphorus for each net, and also the cost of implementing each net. This data is particularly helpful because we have limited resources, and with the large-scale implementation of new technologies, concerns on the feasibility and sustainability of nets are being raised. And as you can see, these nets have varying impacts on the resources. Some nets will require more of one resource than the others. It's also useful to note that the negative values mean the net has an opposite effect. For example, for energy, a negative value means net energy is produced rather than consumed. Since nets have varying impacts on resources, it's important to consider sustainable development when choosing a portfolio of nets. Let's now move on to mathematical programming and superstructure models. Mathematical programming is a powerful process integration tool for the large-scale implementation of technologies. Examples of mathematical programming applied to nets are shown. For example, a linear program was used for optimizing enhanced weathering networks via a source sink model. And then Nang and colleagues into 2020 ranked nets under uncertainty considering technical status, potential capacity, cost, and energy requirement using nonlinear programming. One approach is by using superstructure-based optimization, which embeds many alternative matches covering all possible interconnections that are candidates for the optimal design. It has many applications such as in heat exchanger networks, sustainable water management, and carbon capture, utilization, and storage. This particular diagram shows the superstructure for a carbon capture, utilization, and storage supply chain network. It shows the characteristic feature of superstructures which covers all the possible candidate connections. Superstructure models can also serve as a powerful tool in integrated nets deployment. To date, no studies have been found on the superstructure-based optimization models of nets under resource constraints, which leads me to the objective of this work, which is to develop a generic superstructure-based linear programming model for the integrated deployment of nets, taking into account resource constraints. The next part of the presentation is the problem statement and optimization model. Given a set of negative emission technologies and a set of resources such as land, water, energy, etc., each net is characterized by its impact on the resource per unit of negative emissions. The problem is to find the optimal amount of negative emission allocation for each net to optimize the cost while achieving a negative emissions target and satisfying the resource constraints for sustainability. The figure shows the superstructure model for this problem. The next slide shows the optimization model of this work. The first equation aims to minimize a linear cost function of the negative emissions allocation. The first constraint ensures that the negative emissions target is achieved. The next constraint ensures that the impacts on each resource, land use, water use, etc., are within the selected limits. This model assumes that the land use among nets is mutually exclusive, and the permanence and sink saturation of some nets are not covered in this model. Let's now move on to the illustrative case study and sensitivity analysis. In this work, 6 terrestrial nets were considered, namely BECCS, AR, SES, biochar, DAC, and EW. The impacts of each net on a per ton carbon equivalent of negative emissions using the low impact values from Smith and colleagues, as shown earlier, were used. The target negative emissions is based on the removal rates of 2.18 and 6.54 gigaton carbon equivalent per year to achieve a atmospheric concentration of 350 ppm. But as discussed, that actual target depends on many factors such as energy decarbonization timelines. But for this case study, a stringent scenario of 6.54 gigaton carbon equivalent per year is selected. The resource constraints were based on the planetary boundaries reported by Rockstrom and colleagues in 2009. For example, the proposed limit for land cover converted to cropland is 15%, and the 2009 status is 11.7%. The difference of that, which is 3.3%, is multiplied with the global land area to get the land area limit of 436 million hectares. The same logic is used in calculating water use. For the energy input, it was based on the reported available BioEnergy supply in 2050, which is between 10 to 245 exajoules per year according to integrated assessment models. For nitrogen, unfortunately, humans have exceeded the recommended limit. However, for the purposes of this case study, we assume a limit of 10% of the proposed boundary, which is 3.5 megatons per year. For phosphorus, the limit is set to 1.5 megatons per year based on the difference between the proposed boundary and the 2009 status. It was assumed that the availability of suitable rock for enhanced weathering is not limited. Solving the model results in an optimal nets portfolio as shown. The model only selects the combination of BECCS, biochar, DAC, and EW and leaves out AR and SES in the profile to achieve the negative emissions target, which is 6.54 gigaton carbon equivalent per year. Among the nets selected, EW has the highest and biochar has the lowest allocated capacity. All the resource constraints are maximized except for water use and phosphorus requirements, which are below their respective limits. And the total cost to achieve this scenario is $3,195 billion per year. Next, we try to see the effect of varying the negative emissions target on the net's portfolio and also its effect on the resources. The figure on the left shows the effect of varying the negative emissions target on the net's profile. Beginning with the low targets, only EW and biochar are initially selected until up to a target of 4.8 gigaton carbon equivalent per year. To further satisfy the increasing negative emissions target above this value, the model eventually taps DAC and BECCS. And we can see that throughout the varying target, EW is given the highest priority among the nets. The figure on the right shows the impact of each net option on the land use at varying negative emissions target. Based on the impacts used, EW has the highest energy input, but EW has insignificant nutrient requirements compared to the other nets, which may explain why EW was prioritized over the others. Among the resources, the nutrients have the most binding constraints, and this was deduced by observing the results for the resources. For land use, we can see that at low targets, the land use constraint is not yet maximized, but at the target 4.8, land use has reached its ceiling. Let's see the effect on the other resources. The same can be said for water use and energy input. For both resources, the constraints are not yet maximized at low negative emissions target. We can also see the impact of each net on water use and energy input. For energy input, the negative region here indicates net energy generated, and these are from the nets biochar and BECCS. For both nitrogen and phosphorus, both are already maximized even at low negative emissions target due to biochar. Hence, there's no more room to select nets that have high nutrient requirements, so that the model prioritizes the nets that have low or zero nutrient requirements like EW and DAC. However, the model chooses EW over DAC even if EW has higher land and input energy requirements. This can be explained by the difference in their costs. Shown here on the left is the effect of varying negative emissions target on the cost, which is the objective function that we are trying to minimize. We can see here that at low negative emission target, between 2.18 and 4.8 gigaton carbon equivalent per year, the increase in cost is slow. But after this point, 4.8, the cost suddenly balloons and increases rapidly. And this is due to the presence of direct air capture. We know that the higher our negative emissions target, the higher impact on our resources, including economic resources. But we can get more information from the sensitivity analysis, like for example, here in the cost, that after this 4.8 gigaton target or level, any additional increase in the target will be much more expensive. We also investigated the effect of varying the resource constraints on the total cost of the nets portfolio, shown in the figure on the right. For each constraint, we varied it while keeping all the other resource constraints constant. Lower constraints means we are tightening the constraints, and higher resource constraints means we are relaxing the constraints. In general, tightening the resource constraints increases the total cost, and relaxing each resource constraint decreases the total cost until a constant value is reached, except for water use constraint, which stays constant the entire time, meaning the cost is not sensitive to changes in the water use. What we can learn from this figure is that the effective range for each resource, where the cost will be sensitive to the changes in the resource constraint. For example, for land use, the cost is affected by land use constraints between these values, but beyond this point 6, the cost is no longer sensitive even if we try to increase the available land use. On the other end of the graph, this area here, beyond the graph for land use, is an invisible region. We have now reached the end of the presentation. I will now move on to the concluding remarks. A superstructure model has been developed for optimizing nets under resource constraints. The model gives the optimal portfolio of nets and their recommended capacities while minimizing the cost and achieving a negative emissions target and resource limits. Varying the negative emissions target results to different net portfolios. For the recommendations, the model has the following limitations which may be considered in future work. Number 1 is incorporating the uncertainties in the impacts of nets on the resources, incorporating uncertainties in the resource limits, incorporating the additivity and mutual exclusivity of nets, and finally, incorporating permanence of nets in the model. This is now the end of the presentation. We would like to acknowledge the Department of Science and Technology Philippines and the Engineering Research and Development for Technology Scholarship. Comments and questions are welcome, or you may also email me at this email address. Thank you very much.